Okay, recording. So we're going to start doing the 3-2 notes. We're going to start from the middle, page 5. And we're going to start talking about numerical derivatives. And we're going to talk about what the calculator is actually doing. Like, how does the calculator actually compute the derivative for you? Well, first of all, how do you find the numerical value of the derivative of the calculator? Let's do that first, and then we'll talk about what it's actually doing. So yes, you can find numerical derivatives at a given point. That's totally possible. For example, let's use the calculator to find the numerical derivative of x cubed at x equals 25. We did this already in the 3-1 notes. I already know that f prime of x, the derivative, is going to be 3x squared. And if I find the derivative of 5, I do f prime of 5, just plugging 5 straight up into the derivative expression, you have 3 times 25, I get 75. So I expect the calculator to say 75 or something close to that. So how do you do it? So here's one way you can do it. This is kind of like the old school way, if you have the old operating system. I don't believe anyone does. Or you might be in a mode that uses the old operating system. Let me pull up my calculator so you can see what's happening. So I'm going to go to TI Smart View. That's makes it easy for me to do it with you guys virtually. And again, if you have any questions, please ask. Please someone put it in chat. If you fall behind, get lost, please let me know, because I want to make sure you're following what I'm doing. No, I don't want that. Okay, it's taking a little time. Okay, great. So if you go to mode, and I have classic highlighted. Classic is the old operating system. So if I just kept it on classic, and if I hit alpha window, well, actually nothing's going to happen. Well, something does happen. And select option 3. So again, alpha window, option 3. You're going to see something that looks like this. It's called nderiv. And what it's asking you to do, it's asking you to type in the function that you want to take the derivative of. So in this case, x cubed. Then you have to put an x in the middle just to tell the calculator that you're taking the derivative with respect to x. What that exactly means, that'll be more clear when we get to, I think, 3.4 or 3.5. Don't worry about that for now. Just put x in the middle. And then you have to tell it what x value you want to substitute, of course 5. So the calculator will give you the answer. So I put x is right here, cube, comma, x, comma, 5. This is the old school way. I'm going to show you the newer way in just a second. You get this, and it's not exact. It's 75.0001. So this is if you're in the old operating system, or if you are in mode and stick with classic, that's what happens. And by the way, you can also call up the nderiv function under math and just scroll down, and it's right there, option 8. So to call it up again, you could do alpha window, option 3, or you could do math, option 8. That's how you can do a numerical derivative in the calculator. And what we just did right now was for the old operating system, or under mode, classic. Now, sometimes classic is good, especially like when you're graphing something that's a really long equation, you want to see everything. Unfortunately, in the more newer operating system, they don't wrap around the lines. I don't know why they don't do that. I wish you could keep the new operating system and wrap around, but the classic wraps around all the terms you write when you're like under y equals and you're typing in a long equation when you're graphing something. So classic's good for that. But we really should be in math print, because it actually does a better job of showing the symbolic expressions, because I want you guys to have that notational fluency. So we have to understand the symbols. So if we go back to the calculator, we'll do this again. I'm going to go to mode. Let me actually clear my screen. And let me select math print. So now I'm in the new operating system. And let me clear all my keys here so you can see everything I'm doing. So again, I'm just going to do the derivative one more time. I'll hit alpha, window, option 3. And now it shows me the symbolic way of doing this. You'll put an X here to show that you're taking derivative with respect to X. Again, you don't quite know what that means. They'll be more clear later in this chapter 3. Then you put the function you're taking a derivative of. We're taking the derivative of x cubed. So you put x cubed here. Again, it's very nice. It shows as a superscript. And then you give the x value that you're actually evaluating it for. You're evaluating it at x equals 5. And enter, and there you go. If you hit math and option 8, same place. You get the same thing. So it's up to you. You could go alpha window or math. Alpha window I like a lot because it has some other cool things like absolute value, sigma notation, you might remember that. There's nothing we're going to talk about called integration. We will not do that until the spring. We'll do integration in the spring, but that's going to be very helpful too. And then logs and change of base. So it's a very nice shortcut window. I think it's one of the best things that TI did with the updated operating system. So anyway, let me just clear that. So you get 75.001. So any questions of how I did that in the calculator? We're okay? And again, it looks like this. D, D, and then it's kind of like a box. There's kind of like this blank space here. Oh. There's like a vertical line, then X equals another box. And what you will put here is you'll put X here. You put X cubed, you put 5 there. So that's what you're doing. This is for the new operating system, which is called math print. The old operating system is called classic. So remember, this is classic. That's math print. So that right there is pretty much all the nuts and bolts for the calculator bit. You got that, you're good. It's not any more complicated than that. Now, there are some ways we're gonna use this feature to kind of as a workaround to some problems. We're gonna see some pretty complex situations down the road, especially when we start doing AP like style problems and AP review. And it might not be very clear how to do those problems, but this will be a great feature, a great workaround. And I'll talk about how we can use that to our advantage, how we can leverage this to our advantage. But we're not there yet. We'll get there. Okay, so let's move on to the next page. So now I'm going to talk about the algorithm the calculator uses. How did the calculator, and why did it give 75.001? Well, how come they didn't give 75? Like, what's the story, right? What is a calculator doing? What is it? Whoever programmed this, what did they do? So it's not actually 100% accurate. So just so you know, this is an approximation. The calculator does not give you straight up the truth. I mean, yes, it's close enough. What it's doing is you're telling it, okay, well, here's, again, I have y equals x cubed, right? Y equals x cubed looks like this. Here's x equals 5, right? We'll call that point P, like we have over here. And of course, at x equals 5, the y value is 125. If you were to plug 5 to the function, you get 125 to the original function. Well, the calculator does, it takes 2 points close to the point of tangency. So close to x equals 5, it takes 2 points. It's going to do 5.001 and actually 4.999. So if you replace a with 5 here, it's simply finding the y value at 5.001 and the y value at 4.999. So in fact, this is actually not a derivative. This is just simply a slope of a secant line. So the calculator, even though it's giving you the value of the derivative, it's actually doing the slope of a secant line. It just so happens that it's giving 2 points that are awfully close together, that you can make that assumption that's close enough to being true to the tangent line. So it's kind of like if I drew a line here and I drew a tangent line, they're close enough. That's why it's an approximation. So that's what it's doing. It's just finding that. Some people will sometimes do this. They'll do at x equals 5 and at x equals 5.001 to find that slope. You could do that too. But this is a little better because it's symmetric. Because you're taking a little bit to the left of x equals 5, a little bit to the right of x equals 5. So it's a little bit better of an approximation than just doing PQ. So what the calculator is doing, just so you know, the calculator is giving you the slope of RQ. That's what the calculator does. We want the slope at P. RQ is close enough. That's close enough. We want the slope at P, and RQ is close enough. This right here is just PQ, which is good too, but RQ is a little better. And if you think about it, it's kind of like you're substituting 0.001. That's for slope PQ. If you plug in a very small value of H, like when H is really, really close. Anyway, that's what the calculator is doing, just so you know. I'm not going to assess you on that, but just good to know. And it explains why it's not 100% accurate. It's just, you know, the 0.001 bit, that's why you have that. In fact, if you were to work that out, let me just do it really quickly. If I were to do 5.001 cubed minus 4.99 cubed and divide that by 0.002, because that's the difference between those two x values, you get the same thing. That's all the calculator is doing, just so you know. All right, let's actually find the derivative of this function and try to graph the derivative of this function and identify the graph of the derivative. So that's what we'll do right now. Okay, we'll use the calculator, so let's just go back again. So let me clear. So I'll alpha window this, option 3, put x here, and it's 1/6 x cubed. Now, just so you know, it just follows order of operations. So the calculator knows to do 1 divided by 6 first, and then times x cubed afterwards. But if you're like me, sometimes I'm a little OCD. You actually could do this. Some people like to do alpha y equals and call up the fraction feature. Some people like to do that. That's fine. Or you can put that in parentheses, up to you. Alpha y equals, again, is how you can pull up fractions. And we're doing this at, hold on a sec. Where are we doing this at? Oh, we're graphing this. Yikes. Okay. I'm not leading you guys in the right direction. My apologies. I thought we had to evaluate this for something at some x value. Okay, we want to graph this. Okay, this is a little different. Okay, I'm glad we're actually talking about this. So, yeah, if I did this, like playing a random number, fine. I get that. Okay, we want to graph the derivative. I understand what they want us to do. Okay. Well, here's what we do. So this is how we kind of trick the system to graph the derivative for us. So go back here again. I'm actually going to do this. 1/6 x cubed. I'm just going to graph y1 first, just so I know how it looks. So hit y equals. So you can see I hit y equals. And then I typed in 1/6, as you see right here. And of course I did x cubed. Now, if I just hit graph to see what happens, there you go, right? Nothing special. Whoop-de-doo. I want the derivative. So here's what you can do. Under y2, hit alpha window. We're going to call it the derivative, option 3. I'm going to put x here. And I could type in the same function, 1/6 x cubed. But when you get really big functions and you have to kind of use it over and over again, especially on the AP exam, because they'll have like 4 or 5 parts, If it's like what they did last spring, where it's gonna be online done at home and there's like only 2 questions, one of the questions I think had like 9 parts. So you really need to know how to plug this in the calculator, because you don't want to type that equation over and over again. It's not terribly efficient. So what you do is you plug in the equation under y equals the original. Under y2, I can do the derivative of y1. How do I call it y1? If you guys forgot, hit alpha trace. Alpha trace, so you can call it anything you stored under any these y1, y2, whatever things. So let's hit y1, and then you do x equals x. You do not put a number there. Do not put a number there. Why am I saying that? Actually, if anyone can give me a good reason why, I'll give you 1 point X credit right now for our quiz this Wednesday.
Because you're not finding the slope of the tangent line.
Thank you. You got it, Connor. 100% correct. Good work, Connor. If I were to put x equals 2 here, or some random number, what's going to happen? And someone put something in the chat. If they beat me. Oh, no answer. Okay. How do you get y1? Oh, someone asked. Oh, y1 was our equation in the example. Sorry. So I have to make that clear. So y1 was our original function. That's where I got y1 for example 5. Now what Connor just said, and definitely I'll give you extra credit point. If you put x equals 2 or some random number, all this is going to give you is just a number. And what is it going to graph? A horizontal line. I've had that happen to some people. Say, I tried graphing the derivative, I don't see a horizontal line. And I look at them like, dude, you didn't graph the derivative. You graphed a number. You graphed the value of the derivative for that function. You got to put x equals x. So what it's going to do, it's going to actually graph the derivative of 1 to 6x cubed at a whole bunch of x values for whatever window you've defined in this calculator. I think my window's from -10 to 10 for x. It's going to be very slow too, just so you know. It's going to be very slow. So let me go back and change it to x equals x. Okay, there's a question in the chat. Sorry, how do you get y1? My apologies. How do you get y1 in the calculator? Sorry if I did that quickly. Hit alpha trace. Alpha trace. Sorry about that. I didn't understand your question in the chat. My bad. So hit alpha trace. Okay, so now let me go ahead and clear my writing here. Let me just clear that out. Okay, so if I hit graph, you can see it graph the second thing, but graph it a little more slowly. Actually, if you want, you could turn off the first equation if you don't want to see it. So go ahead, hit the equal sign. Sorry, move to the equal sign and just hit enter, and it toggles it for you. And see, it just does a little more slowly, and it's actually a parabola, so it seems. So that's what happens there. So that's how you can graph the derivative, and it's a parabola for sure. So we have this. And if you want to identify, I know the derivative of x cubed was 3x squared when f of x equaled x cubed. So I probably suspect for this right here, the derivative probably will be 1/6 times 3x squared, or x squared over 2. If I were to go back to the calculator and kind of investigate that just a little bit, like if I trace, like at x equals 1, it looks like it's about 1/2. At x equals 2 should probably be 2. At x equals 3 should probably be about 4.5. At x equals 4 probably should be about 8, I think. Yeah, so you know, it's kind of nice to explore that. Now, what can we do to help identify the graph of f prime? So let's move on to the next page. Just give me 1 sec here. I need to pull my fold out notes. Sometimes I forget other annotations I need to tell you guys. Give me 1 second here. Calculus AB, lecture notes, filled out, 3, 2. Yeah, basically what I just said here. You kind of trace. Look at the points. Now, yes, there's a more accurate way you're going to do this. We're going to talk about that on Wednesday. Okay, so let's do a couple more examples before we end class today, because I do want to get into page 7. So now your calculator can be misleading sometimes, just so you know. The calculator is not 100% honest with you. So you do have to be a little skeptical. For the most part, 99.9% of the time, it's going to be honest with you. This is the 0.1% it's not honest. Use your calculator to find the numerical derivative of that. Well, okay, so let's do this. Let me go back to my calculator again. Go to y equals. Let me go ahead and clear that. And here's a nice thing. I don't need to keep typing in this over and over again. I could just type in a new equation of y1, and y2 takes care of the derivative for me. So let's do absolute value of x. Remember, alpha window is where you can call absolute value, or if you hit math and then num, it's right there. We're doing x divided by x. There we go. Now, if I hit graph, and it's interesting. I didn't really see the derivative there. Let me turn that off. So it's very interesting. I didn't see a derivative. So what gives, right? Anyone know why I didn't see something? We'll give another point of x credit if anyone knows why I didn't see something.
Because the derivative doesn't exist because it's not continuous.
At x equals 0, what about the other parts? So let me turn this on again. Let me turn off the derivative. You're 100% correct about this part, but what's the derivative on the right side here? 0, right? What's the slope here?
0.
And the slope over here is also 0. So when the graph's a derivative, actually it's graphing it. You just can't see it. What is it graphing?
Is it just on the x-axis?
Good. I'll give you the extra credit point. Thank you, Nico. Yeah, it's just on the x-axis. It's actually there. You don't see anything, right? Hit trace and just hit the right key. It's there. And it shows you right there as well. Now at 0 shows you nothing. Actually, no, 0 shows you something. It's interesting. Shows you 1,000. That's weird. What's happening there? I thought it doesn't exist at 0. So let's explain what's happening. So actually, if I go back to the home screen, let's go alpha window, option 3. Crap. Option 3. X. And put alpha trace, y1. And let's evaluate x equals 0. It says it's 1,000 for absolute x over x, but I know it's undefined or does not exist. What is the calculator doing? So the calculator tells us this. That's 1,000. But we know it does not exist. Why does it not exist? Because it's not continuous, right? So here's a graph of f of x. And we know we're not continuous at x equals 0. What the calculator is doing, just so you know, it's doing this. Remember I told you the algorithm it uses? That's what you have to understand what the calculator is doing. That's why I spent that time talking about that. Again, I'm not assessing on what the calculator is doing, but you need to know that. So the calculator is actually finding the slope between these 2 points here, which is very steep, and that's why it's calling it 1,000. So the calculator is lying to us. It's very stubborn. You know, just does it, and that's that. So it doesn't have a brain so much. So so you have to be very careful about that. It can be misleading. So any questions about example 6 before we get to the home stretch here? Okay, let's talk about example 7. We're going to look at a problem like this one here that's kind of weird. It's got x minus 3 to the 2/5 power. Remember, we did spend some time talking about, you might remember earlier this semester, we did this worksheet. On power functions. And how to graph how to graph in the first quadrant based upon whether the exponent was like, you know, positive, it was like bigger than 1, between 0 and 1, or if it was like negative. And we have all these different like situations here. That's why I spent that time doing that, because I really want to make sure you understand how these graphs look before you start applying these calculus principles. And now we're applying a calculus principle. We're doing derivatives. So we're there. We're doing this now. So I was, unlike the calculator, I was honest with you. I told you that we're going to do this, and we are doing this. So here we have this graph. It's going to look a little weird. I'm going to graph it for you. Actually, I'm going to graph it by hand, but I'll do it in the calculator anyway. I mean, yes, graphing the calculator is fine, but it's just good to understand why it looks the way it does when you understand power functions. So this is an exponent that's a fraction with an odd denominator and an even numerator. We talked about generally how those look. Those kind of look like this. When you have like y equals x to the n power, where it ends between 0 and 1. We talked about that again on worksheet 1 a while ago. And then of course, if you can define it for a negative exercise, which you could, because it's an odd denominator, so you could plug in negative, because you could fifth root negative numbers. So you have this here, and then the minus 3 shifts 3 right. So that's how I can actually graph this without using a calculator. Nothing special I'm doing, just I understand how power functions look. If I plug in 4, I think I get 1. 2, I get 1. So you get something that looks like this. Again, if you want to graph the calculator, you totally could. But what I just did is I used my knowledge of power functions to do the parent function, x to the 2/5, and I did a shift of 3 right. That's what I just did. So now we're asked to show that this is not differential at x equals 3. So we have the original right here. We're going to graph the derivative, and we're going to establish left and right hand derivatives. So these are left and right hand derivatives right here, LHD and RHD. And then we're going to determine if any of these things are happening. First of all, I know it's continuous. So it's not that one. Just look at it. It's continuous. Plus, I could plug in 3. What's the problem? I could fit through 0. Who cares? And just by looking at it, the limit does exist at x as x approaches 3. It's going to be 0, and it's the same thing as f of 3. And again, if you're not sure, if you're still a little uncomfortable with power functions, that's okay. Just do x raised to the 2/5 power. Sorry, I meant to say x minus 3. X minus 3 raised to the 2/5 power. And I'm going to turn off the derivative right now. I just want to look at the original graph. Yep, there we go. There's my original graph. Now I'm going to turn off the original graph and turn on the derivative. And here's how it's going to look. It's going to be a little slow. So it looks like it's drawing a rational function. Kind of like this. So let's go back to this here. So again, our graph looked like this. That was our original graph. The derivative graph looked like this. At x equals 3, we notice an asymptote. And it looked like this. What's happening is that the slope of the tangent lines are negative to the left of 3. The slope of the tangent lines are positive. Let me actually do green for that. Are positive to the right of 3. We see that, and then remember, when you have the graph of the derivative, the y values of f prime graph are the slopes of tangent lines of f graph. Sorry for the messy handwriting. The slopes of tangent lines of f graph. And the slopes of the tangent lines are derivatives, right? This is what we've been talking about the whole time. So just notice as I get closer to x equals 3 from the left side, what's happened to y here? It's shooting down forever on the derivative graph. If I get closer to 3 from the right side, it's shooting up forever on the derivative graph. So what's happening is that this is going to be negative infinity. That's going to be positive infinity. Therefore, we have a cusp. That's how you can tell. That's how you do analytically. Well, graphically, and you connect it to the analytical part. Actually, to do analytically, I lied. You got to do the derivative by hand, which we will do down the road for something like this. And there's a shortcut that'll help with that, which we'll explore that later. For now, we're doing it graphically. So again, you had to find the left-hand derivative, which was negative infinity, the right-hand derivative, which is positive infinity. And so that's a cusp. And remember, we did establish continuity first. We did do that. We did do, f of 3 existed. The limit as x approaches 3 from either side was going towards 0. But the left and right-hand derivatives don't equal each other. And one is negative infinity, the other one's positive infinity. So that's what's happening there. So again, for now, we're going to go based on a graphical interpretation. I think is better. We will get to the more analytical, like analytically, you'd actually have to plug this into the derivative formula we have. The limit as h approaches 0 of f of a plus h minus f of a over h. That's kind of painful to do. So the shortcut rules, which we'll do in 3.3, will help with that. And we'll revisit this problem when we do the shortcut rules for derivatives. And then you would see analytically, oh yeah, of course the left-hand derivative is negative, of course right-hand derivative is positive, of course it's not differential x equals 3. So that's what's happening there for that one. Okay, I think it's a good place to stop. It's 10:09. Class is over about 1 minute. So I will do a video later this afternoon on, I have to because you guys have to do homework. Now, if you're taking the SAT on Wednesday, don't worry about homework. Do it later. Turn to me on Friday. Focus on the SAT. Get some sleep on Tuesday night. For someone who's spent 19 years in test prep, I know how important that is. It's a little weird it's on a Wednesday instead of a Saturday, but hey, just things are weird this year. It's the pandemic, right? What are you going to do? But don't worry about the homework for my class. If you're taking the SAT this Wednesday, do not worry about the quiz. Do not worry about getting homework to me on time. Hopefully your other teachers feel the same way. I don't know. Maybe I might send a quick blast out to some of the administration, say, hey, just heads up, maybe we should consider this because I want you guys to do well on the SAT if you're taking it, right? It's even though law school's gone test optional, it's still a good data point if you can do it. So anyway, that's that. I will stop this recording. And homework again, I will post. So I'll do a video on pages 8 and 9, and I'll probably just do a few textbook, not much, just a few. And then on Wednesday, what we'll do is we'll recap the stuff. We'll probably do a 3.3 video lesson, and then we'll have the quiz near the end. And then there'll probably be some homework to go back and look at 3.1 and 3.2 again. And 3.3, we'll probably spend more time on that next week as well. And there'll probably be some homework over the long weekend. They'll do more 3.3 and more 3.3 problems. So we're getting to 3-3 very soon. But for now, we have to wrap up 3-2. Okay, I'm all done. You guys have a good rest of the day, and I'll see you guys later. Bye.
Yeah.
Thank you.